Start with the basics. A single positive point charge emits an electric field radially outward in every direction. But if we take that single point and stretch it out into an infinitely long, uniformly charged wire, the field lines behave differently. Calculating the electric field for this structure using standard Coulomb's law is a burdensome task. The standard integration method requires you to break the wire down into infinite tiny charge elements, denoted as dq. Each microscopic element produces its own field vector at your observation point, resulting in a dense, overlapping web of intersecting lines. Because the distance and angle from the wire to the observation point change for every single one of those elements, the resulting integral is mathematically heavy and highly sensitive to error. While brute force integration can solve this, there is a more elegant method for systems involving infinite continuous charges. We can bypass the complex calculus by analyzing the physical geometry of the wire itself. This is where we apply Gauss's law. Gauss's law allows us to translate a system's spatial symmetry directly into an algebraic equation. To apply it, we must define a Gaussian surface, an imaginary closed boundary that we construct around the object to measure the field passing through it. Finding a boundary shape that aligns with the symmetry of the wire reduces the math to its simplest form. Before choosing our Gaussian surface, we have to establish the precise direction of the electric field. Consider an infinite wire and a random observation point, point P, in the space next to it. Now select two arbitrary equal charge elements on the wire that are equidistant above and below point P. Because the wire is infinite, every charge element above the point will always have an identical counterpart an equal distance below it. If we resolve their diagonal vectors into components, the vertical components of these twin vectors are equal in magnitude but opposite in direction. They cancel each other out. However, the radial components point in the same direction and add together. Applying this to the entire infinite wire, all vertical components vanish. The overall electric field can only point radially outward. This radial symmetry dictates the exact shape we must choose for our Gaussian surface. We need an imaginary 3D boundary that matches this radial symmetry. A cylinder is the appropriate choice. We will define its radius as r and its length as L. For the math to work, the electric field must be either parallel or perpendicular to the surface's area vectors. We calculate the electric flux as the dot product of the electric field vector and the area vector. On the flat top cap, the area vector is vertical, while the electric field is horizontal. They meet at a 90-degree angle. Since the cosine of 90 degrees is 0, no electric flux passes through these end caps. On the curved side of the cylinder, the area vectors and the electric field vectors both point radially outward. They are perfectly parallel. The cosine of 0 degrees is 1. And because every point on this surface is exactly distance r from the wire, the electric field has a constant magnitude. The surface area of this curved portion is 2 pi r times the length L. The total flux through the system simplifies to the field magnitude E multiplied by this curved area. Gauss's law states that the total flux equals the enclosed charge divided by the constant epsilon naught. Next, we must determine the exact amount of charge trapped inside our imaginary cylinder. We use the linear charge density, lambda, which represents the charge per unit length. The enclosed charge is simply the charge density multiplied by the length L of our cylinder. Now we equate our flux expression with our enclosed charge expression. You'll notice the length variable L appears on both sides of the equation. As L cancels out, the dimensions of our imaginary boundary vanish from the calculation. This shows that the final result depends only on the source charge itself, rather than the dimensions of the arbitrary boundary we use to analyze it. Isolating E gives us the final formula for the electric field of an infinitely long charged wire. Compare this to the formula for a point charge. The difference lies in the denominator. The point charge field depends on r squared, while the line charge field depends only on r. This graph illustrates the effect. A point charge field fades rapidly, but the line charge field decays much more slowly over distance. The geometry of the source charge determines exactly how its field strength reaches across space. In reality, infinitely long wires do not exist. For a finite rod, the perfect symmetry we assumed breaks at the ends. This warping at the edges is called the fringing effect. The formula we derived remains accurate as long as your measurements are taken in the central region of a long wire. These symmetrical mathematical models provide the necessary foundation for understanding the behavior of fields in more complex real-world systems.